Hello. Yesterday, in the last video, we talked about linear subspaces and bases. Today, we talk a bit more about bases, and then we move to the study of the determinants of a matrix. So this video's content corresponds to chapter 3.2 of the book. Next videos will cover chapters 3.1 and 3.3. So a linear independent base subset of Rn must have at most n elements, and a spanning set of Rn must have at least n elements. So every basis in Rn has exactly n elements. For an element subset V1 through Vn of Rn, the following statements are equivalent. So a vectors V sub I span Rn. These vectors are linearly independent. They form a basis. And the square matrix whose columns are those vectors is invertible. So take a minute and absorb every claim from here, and then make sure that you understand why each of the statements is true. From a basis V1 through Vk of a linear subspace of V of Rn, so it's a dimension, it's a vector V is generated by the basis, we can define a linear map T from Rk to Rn that takes X and maps it into a matrix which is formed by column vectors V1 through Vk multiplied by X. So by construction, this linear map has range V, since all Vi span V, and it is one-to-one, because the vectors are linearly independent. A basis for V is essentially the same as a one-to-one linear map with range V. And this is also called an isomorphism from Rk to V. So isomorphism means that it's one-to-one and onto, right? So every two elements have different preimages, and the range coincides with the codomain. Suppose we have two bases, V1 through Vk and W1 through Wl, of the same linear subspace V of Rn. Now, consider a linear transformation T from Rk to Rn, which is the standard linear map, which takes X to the matrix, which is formed by columns, whose columns are vectors Vi multiplied by X. Since T is one-to-one with range V, there is a unique element of Rk which maps to Wi. So let's write this as T inverse of Wi. And then, of course, if you apply T again, you'll get Wi back. So given a linear dependency, excuse me, so if 0 is equal to sum of some coefficient Ci times T inverse of Wi, we obtain that T of that linear combination, since it's a linear transformation, we can make it as we can apply T to the each of the vectors and then sum, and then keep in mind that T of T inverse of Wi is equal to Wi, we get the right-hand side. The Wi's are linearly independent, therefore all the coefficients must be 0. So thus the preimages of those Wi's are also linearly independent. Now, since the Wi's span V, each vector V sub j can be written as the linear combination over vectors Wi. So we have a coefficients with double index I and j, and here are the sum ranges in I. Now, remember that by definition, if you take the vector ej from the standard basis, and apply the transformation, there we get Vj. So T of Vj is equal to sum of, so that's equal to Vj, and that's using the top formula is equal to sum of Cij times Wi over here, and then Wi is equal to T of T inverse Wi, and then we can move T up front to get this. Now, because it's 1-to-1, we can claim that Ej is equal to, so now we can apply T inverse to here and T inverse to there. So T and T inverse cancel each other, and then we get that Ej is equal to sum Cij times T inverse of Wi. And therefore the span of the T inverse of Wi contains all vectors Ej. And therefore it contains all Rk, the entire set, entire vector space Rk. So therefore, there are as many W's as element of the basis Rk, namely, so i.e. the Rk of them, right? So, which is the same as the number of Vj. And therefore we have proven that every basis for a linear subspace has the same number of elements. This common number is called the dimension of the linear subspace. So you may have different bases, but as long as it's a basis, it has to have the same number of elements, no matter how you choose the basis. Now, recall last time we talked about null space or kernel, and there's this statement that's called rank nullity. So if A is a matrix with R rows and C columns, so it determines a linear transformation from C-dimensional Euclidean space to R-dimensional Euclidean space, then the dimensions of the column space and the null space add up to C. And the proof is really elementary. You don't need to write any formula, simply because the column space has dimension equal to the number of pivot columns. So once you reduce it to the echelon row, to the echelon form, so the pivot columns here, they span the column space, and the null space is spanned by the non-pivot columns, which are all the other columns. So altogether, we have C. They add up to C. Another theorem, the dimension of the space spanned by the rows of a matrix is equal to the dimension of the space spanned by the columns. Why is that? Well, simply because both are equal to the number of pivots. Right? So it doesn't matter how you count pivots, horizontally and vertically, or vertically. Now, in connection with invertibility, if you have a square matrix, so when R is equal to C, then the following statements are all equivalent. So the matrix is invertible, rows are linearly independent, rows span, rows form a basis, and same with columns. So columns are linearly independent, the columns span, columns form a basis, it's a one-to-one transformation, and it's onto. So remember that the last two statements mean that there is an isomorphism. So all these conditions, they collapse into this big list. Okay, let's check. You can quickly check yourself using these examples. So pause the video if you need more time. So is this matrix invertible? Well, clearly the answer is no, right? So you cannot get it if you remember how to do. So no matter what, no matter what you do with this row echelon reduction, it's impossible to make it the answer is no. Then this matrix is yes, right? It's the identity matrix, it's the inverse of itself. This matrix, well, you need to reduce it to the echelon form. And then if you do that, you see that the first first row is proportional to the second row. So if you multiply the first row by 3, you get the second row, and then the reduced echelon form will look like this. And this is clearly not invertible, right? Because there's only one pivot and 2 rows. Okay, and in the first example, there are no pivots at all, right? So, so there's no like yeah. And this one, it does, right? So if you reduce it to the echelon form, you see that it has exactly two pivots. Okay, now we'll get into the notion of the determinant. Well, we talked about this last time when we looked at the formula. So is the matrix with the generic coefficients A, B, C, and D, just some real numbers, invertible? So if A is not equal to 0, so we need to look at some particular cases. So if A is not equal to 0, then we can do the standard row reduction procedure like this, right? So we get the first pivot column. So the matrix is invertible if and only if AD minus BC is not equal to 0, right? So that we will have 2 pivots. Okay. Now, if A is equal to 0, then we need to, well, we cannot use it as a pivot anymore. So we need to use the second row as the pivot, so we can swap them around. And then by inspection, the matrix is invertible if and only if B and C are not both 0, right? Because so if A is equal to 0, because 0 B C D, you can rewrite it by swapping rows as C D 0 and B, right? And then if C is 0, then we're done. It's not invertible, right? Then there's the first column is 0, so it's not a pivot column. If B is 0, it's still okay, right? Because you can yes, I'm sorry. If B is 0, yeah, if B is 0, it's also not okay. So yeah, so if C and B are both, yes, if B and C are not equal to 0, so if C is non-zero and B is 0, then it's a problem. And if C is 0, it's also a problem. So I'm gonna remove both here. There's a typo. So neither of them is okay. So each of them has to be non-zero. Okay. And then in short, the matrix is invertible if and only if this combination AD minus BC is not equal to 0. And we call it the determinant of the matrix. The determinant of the 2 by 2 matrix is the first element, 1, 1 element times 2, 2 element minus 1, 2 element times 2, 1 element. So it's AD minus BC. It's now denoted as determinant of this matrix, if you call it A. Well, let's do the calculation. In this example, well, there are no pivot columns, but let's use it. Let's calculate the determinant. Well, clearly the answer is 0. Here, again, a simple calculation. A equals 1, D equals 1, the rest is 0. The answer is 1. In this example, the answer is 0, right? Because the rows are proportional to each other. In this example, it's not 0, it's equal to -1. So therefore, the matrix is invertible. Okay. How about this one? Yes, there are 3 pivot columns, right, in the 3 by 3 matrix. This matrix over here. Yes, right, it's also it's not in the reduced echelon form yet, but we can make it one. We can reduce it there, and then the reduced echelon form of this matrix will be exactly as the matrix above, right, after we've done all the necessary calculations. And this one, also yes, right? So to do the, it's basically you need to swap rows and columns around and then do the echelon thing. So we can write it as the third column first, 3, 5, 4, 2, 2, 0, 8, 0, 0, and then we'll do the standard procedure with eliminating rows, excuse me, with the row reduction, so that it will take the pivot form. And in the pivot form, excuse me, it will take the echelon form, and in that echelon form, you will see that we'll get 3 columns, 3 pivot columns. How about this one? 1, 2, 3, 1, 2, 3, 4, 5, 6. No, right? Because 2 first rows are proportional to each other, and by row reduction, one of the rows can be made to be equal to 0. 1, 3, 4, 1, 3, 2, 2, 6, 8. No. Again, try it for yourself. So do the echelon reduction and convince yourself that it doesn't work. So in particular, you can see that if you multiply the first row by 2, you get exactly the third row. So it is not invertible due to the same reason. How about this one? Well, you need to do the calculation, and the answer will be no. So you can find a combination of rows which would so the reduced echelon form will not be will have 2 pivots instead of 3. Okay. Now we can answer this question again. So in 2x2 matrix case, we were able to answer to reduce the invertibility question to whether the determinant of the matrix is 0 or not. Now let's see if you can do the same with 3x3 determinants. Take a 3x3 matrix with 9 entries, A, B, C, D, E, F, G, H, I, and let's ask ourselves, when is it invertible? Again, we need to make some assumptions. For simplicity, assume that A is not equal to 0. And then we're doing the row reduction. So we get rid of the second row and get rid of the third row by making the necessary linear combinations, right? So we multiply first row by minus D and add it to the second row, and multiply it by minus G and add it to the third row. So that gives us the first pivot column. Now, this matrix is invertible if and only if the bottom 2 rows are linearly independent, right? So because we know that so we already gained 1 pivot column. So the only thing remains is to understand what's going on in this 2x2 matrix. So when is this invertible? Well, when the determinant of this 2x2 matrix is not equal to 0, right? And we know how to calculate it, right? So we take 1, 1 element multiplied by 2, 2 element, and subtract 1, 2 element multiplied by 2, 1 element. So that's written in the next row. And then after a little bit of algebra, which I encourage you to do by yourself, you get that it's equal to A multiplied by this the parentheses, which includes 6 terms. 3 appear with plus sign, and 3 appear with a minus sign. So it's a cubic expression. Each of these terms is a product of 3 numbers, 3 elements from the matrix. So since we assume that A is not equal to 0, we know that the expression above is not equal to 0, if and only if we can cancel A, so that the expression in the parentheses is not equal to 0. And this is called the determinant of that matrix. Now, only now this matrix is 3 by 3. So let's figure out, let's find a way how to calculate the determinant without doing the echelon reduction, right? So this is the formula here. So again, it's AEI. So you take the product over the diagonal, right? And then you do BFG. I'm going to color them in different colors, and hopefully you'll see some pattern here, plus CDH. Okay, so these are basically I took the product of elements on the diagonal, and then I took the product of, well, you can see it by yourself. Like it's like elements that look at it in a triangle, which looks like this. Like there's a yellow triangle, and there's also green triangle like that. Okay, so that gives us 3 terms which enter with a plus sign. Remember that, right? So basically, and now let's write, okay, I'm going to draw another matrix here. Let's see what's going on with the terms would have minus sign. Minus ECG is elements of this diagonal, okay, and then minus AFH over here, and finally minus BDI, which elements over here. So again, you can see the structure that you have 2 opposite oriented triangles and a diagonal. Right, so therefore, sort of this, it gives you some mnemonic rule of how to memorize the formula for the determinant. So let's call this matrix A. Determinant of A is equal to this. And sometimes this formula is called star formula, or like this method. Because if it actually looks like a star, right? So if you kind of look at the diagonal, and then there's a triangle, there's a green triangle going this way, there's a yellow triangle going that way, and then that gives you first 3 terms with the plus sign, and things with the minus sign, they have a different orientation. So the diagonal now goes from the bottom left to top right, and then there are 2 triangles like this. And then of course here, well, you can also check that we assume that A is not equal to 0, but in this formula it doesn't really matter. So if A is equal to 0, the formula still stands. It's just 2 out of these 6 terms will be equal to 0. Okay, so here is another sort of visualization of how this works. So in 2 dimensions, if in 2 by 2 case, it's AD plus minus BC. So again, it's diagonal, and then, well, sometimes this is called anti-diagonal. And this is diagonal. They both exist for any square matrix. Okay, and in 3 by 3 case, it's the star formula, which I illustrated for you before, and here it is for you again, right? So the pluses appear as the diagonal, and then 2 triangles that go next to it, and then the minuses appear from the anti-diagonal and the 2 adjacent triangles. Okay. Now, how about arbitrary matrix of arbitrary square matrix of the size n by n? Well, then it's a sum. So we need to, so the idea, of course, is to start with matrix n by n and then reduce the computation of the determinant of this matrix to the determinant of a smaller matrix. And then again and again and again until you get through all the numbers on all the elements. So over all ways of choosing n entries of the matrix such that one is in each row and each column. And then we take the product of those entries with some signs, right? So see here in 2 by 2 case, we took element A from the first row and first column, and there was nothing else from that row and that column. And then element 2 was taken from the second row and second column. That's one way we can do it. Another way to do it is that we take element C from like this. So from the first row, second row, and maybe I should count with rows. And so first we picked the first element A was the first element in the first row. So we did this choice, and then the only element which was left was D, because we need to take an element from not from the first row and not from the first column. And then in the second choice would be that we take the second element in the first row. So therefore, first row and the last column are fixed. Sort of, we cannot take from there anymore. And we just need to take a C as the remaining one. So it turns out that with the sign convention, AD enter with a plus sign and BC enter with a minus sign. So in 3 by 3 case, well, let's see what's going on here. So we take the first row and we take the first element in that row. So we fix the first row and first column. Now we take the second column, second row, and then since the first element we cannot take anymore because it was otherwise we would have taken 2 elements from the same column, we want to take either the second or the third. So if you take the second, we take E, and that works. And then finally we can take I. So this goes with a plus sign. And then here, so the rest of the terms, they represent different choices, right? So if you take first row and take B here, the second element, right? And then we have, well, 2 choices to make. So either we take, in the second row, we take the third element, or we take the first element. Excuse me, it was from the other one, so B here. So yeah, say we take B, and then in the BFG term, we take the third element from the second row, and in the BDI element, we take the first and second row, and so on. And then we just take the remaining one. So each of those terms, they work like that, right? And then there is a certain prescription of the sign, which I'll talk about in a second. Well, now, given the choice of n entries in an n by n matrix with 1 in each row and each column, an inversion is a pair of these entries, such that the row of the first is before the row of the second, but the column of the first is after the column of the second. So in other words, it's the numbers of arrows which goes from bottom left to top right that you can draw connecting one entry with another. So see how it goes. So here, well, in the second example, we can draw an arrow like this, a vector from C to D. And on the left, we cannot do that, right? So like there's nothing we can do. So here, there are 0 arrows, and here there is 1. So therefore, we have -1 to 1, which is -1. Okay. Now, in the 3 by 3 case, again, so here are the numbers of rows that we can draw. So here, well, we can draw 2 arrows this way, 2 arrows that way. Here we have 1 arrow, 1, and here we have 3, right? Because yeah, so like this is what we discussed before, right? So the column should appear after, and the first example there is 0. Okay, so that can be understood again as one of the mnemonic rules, but of course there's a formula, right? So the sum of all ways of choosing n entries of the matrix such that 1 is in each row and in each column, the product of those entries times -1 to the number of inversions. And inversions is this number of those errors that we counted. So that's what happened. Let's look at this again. Okay. And so that's what happens in 2 by 2 case. There's 0 inversions for the first term and 1 inversion for the second term. And the same in 3 by 3 case, right? So the here there are 0 inversions. Here there are 2 inversions, 2 inversions, 1 inversion, 1 inversion, and 3 inversions. So like think about inversion as like how many times you broke this normal order, right? So here in the first example, everything is ordered properly, right? So you take first element from first column, first row, and then second column, second row, third column, third row. So here in the second example, you altered it twice. And again, in this third example, you also altered it twice. However, so we have the first row here gives us an even number of inversions, and the second row gives us the odd number of inversions. Okay. Now look at this matrix. So it does remind you the telephone pad, right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the determinant? Well, again, pause the video if you need some time. Well, we can do it here, right? So first do it by yourself, and then look at the video, the rest of the video. Right. So we have 1 times 5 times 9 plus 8 times 2 plus 6, 2 times 6 times 7 times 3 times 4 times 8 minus 48 minus 72 minus 105. Can you add this together? What is it? Bam, it's 0. Right. So the well, I mean, it's easy to sort of that gives -3, right? This gives 12, and this gives -9. Yeah. So this matrix, the determinant of this matrix is equal to 0, which means that it is not invertible. Now, for larger matrices, like there is no simple star-like formula, so you have to look at some at the linear at this recipe that I just told you. However, well, notice here that there is an arrow of only zeros, right? What does it tell you? Think about it. After you come up with the solution, continue the video, right? Because of this fact, the every single term. So every time, every element in this every term in the formula for the determinant contains always one element from this row, and it just everyone is 0, right? So you multiply it by 0, so like you add a bunch of zeros. So therefore, the determinant of this matrix is 0, and it is not invertible. So it's easy to see that it's the case. You don't have to write down all the terms to prove that. Okay, now let's look at this one, right? So we have another 6 by 6 matrix, which, well, given in this form, right? So how would you do the calculation in that case? So course, we need to take into advantage that there are this many zeros in the below the main diagonal. Okay. So now we need to identify all the terms which will not be zero, right? So in the formula for the determinant, so the only way to choose an entry from each row and each column without choosing zero, is to choose the entries along the diagonal. And because, so if there's an element you can do, so that product with plus sign will enter the formula for the determinant. And if you do any other choice, right, anything else, so say you can pick elements for here, but now you cannot pick any element neither in this column nor in this row. So therefore, you have to take at least one element elsewhere, not from the above, right? So, and you have to pick at least one zero. So therefore, every other product of 6 elements from this matrix will have to contain 0. And for the answer is just the product of the diagonal elements, which equals 720. Okay, now let's see what happens with the determinant if you do some elementary operations. So multiplying a row by a constant lambda. Well, and then more generally, any matrix with no entries above the diagonal. Well, I believe the slide went. Yeah. So So what is the determinant of this, right? So we rescale the row, right? So then the determinant. So let's say matrix A was A, B, C, D, E, F, G, H, I, right? And then what we're doing, we're multiplying the first row by lambda, and as we know, every time we calculate the determinant, we'll have one element from the first row, right? So therefore, it will be just lambda times the determinant of A. So if you multiply one row by lambda, it will scale by lambda, and then you can multiply, for example, another row by mu. It will also scale here. Try to explain why. And yeah, so if you have the triangular matrix like this, with all zeros, with non-zero entries above the main diagonal, then its determinant is the product of the entries on the diagonal, because of the fact that we just discussed that any other way of selecting one entry from each row and each column must pick a zero. Okay. So this is the illustration for the exercise that we had. So I believe the slides here have been altered. I'm going to change it in the handout. But yes, if you multiply the first row by lambda, then the determinant scales by a factor of lambda. So that's what happens when you rescale a row. And more generally, the same is true for a square matrix of any size, right? So if you multiply a row by a number, then it scales the determinant by the same factor. Each term in the determinant is a product of entries, one from each row, and hence containing exactly one from the rescaled row. Similarly, rescaling the column likewise rescales the determinant. Now, the linearity in rows, right? So let's say, can we express this? So we have the first row, we have in each entry, we have sums of two terms, A plus A prime, B plus B prime, C plus C prime. Well, here's our star formula, right? So every term here contains some, well, whenever we pick an element from the first row, right, it multiplies by the rest of the EI or FJ or DH and so on. But then we have this expression, this 6 terms, right? And then of course you can just expand it, right? So you can open up the parentheses in each of those expressions and yeah, expand it. And then instead of 6 terms, we have 12 terms, which can be conveniently combined into the determinants of 2 3x3 matrices. Well, generally, the same is true for any square matrix of any size, that the determinant is linear in any given row or column. Same can be done for column, right? So, so here R's are vectors, R1, R2, and so on. And now if you take the kth row, right? So you have sum of 2 vectors, ARK plus BRK prime, then you get the right-hand side. It will be A times the determinant of the, well, the first matrix plus B times the determinant of the second matrix. Okay, so here's the formula. Yeah, each term in the determinant on the left is a product of entries from each row, and therefore 1 in the kth row, and then it will decompose into sum of two entries, which you can again combine into determinants of the respective matrices. Okay. Okay. Now, interesting fact here. So what happens if you don't do that? So if you, well, this was a rule about adding elements in the rows, in the same row. Now, if you do it in different rows, it's not so easy, right? So it's not going to work like this. So clearly, if you take identity 2 by 2 matrix, 1 0 0 1 is equal to 1 0 0 0 plus 0 0 1 0 1. But of course, the determinant of identity matrix is 1, and these determinants are 0. So therefore, it does not enjoy such property. You cannot do it for the whole matrix at once. So the determinant is a pretty complicated combinatorial structure, right? It only has very special properties for row and column transformations. Okay, so again, how about this matrix? We talked about its invertibility, so probably its determinant will be, so it's 1 2 3 1 2 3 4 5 6. Now we talked about this matrix is not invertible, so its determinant should better vanish. Let's check it using the calculations, right? So the diagonals, and then those triangles, and then the negative signs, the triangle here, triangle there, and the anti-diagonal, and of course everything cancels. So it works like this as well. Any matrix with a repeated row has determinant 0. It can be proven either by, it can be shown directly from the calculation, right? So that the repeated rows are in positions I and j, and then for any term in the determinant with selected entries in positions I, x, right? So it's the x column and j, y, so it's the j's row, y's column. There will be another term with the same selected entries on rows, all rows except I and j, right? And in this row, in these rows, the entries will be I, y, and j, x, and then of course they will cancel, right? So the I and j rows are the same, so the terms are products of the same numbers, but one of them has exactly one more inversion than the other, so therefore they have to have overall minus sign, and therefore they will cancel. I encourage you to look at the previous example again, and then understand why this is the case. Right, so let's do it 1 2 3 4 3 4 1 2. So one determinant is -2, the other is 2, and you can see that the difference between those matrices is that you swapped the first row and the second row. Let's see what happens when we swap rows. So if you only swap first and second and first, then the determinant changes sign. Why is that? Well, again, you need to look at the number of inversions, right? So consider a term in the expansion of the determinant to the left, and it contains the entries 1x and 2y. So it's the first row x column, x's column, and second row y column. And on the right, it will contain entries 1y and 2x, and all others are the same, right? So therefore, it's a product of the same numbers, except that including all the inversions, except that these two elements is an inversion. So 1, x and 2, y is an inversion if and only if 1, y and 2, x is not, right? So pretty much there's only one way to do it. So either on the left you have them in inverted order, then on the right you have them in the non-inverted order, or vice versa. But regardless, signs will be different. So they have opposite signs, and bingo, this minus sign appears in front of the denominator. Okay. Now let's do this. Let's do the linear combination. So add a to the second row, first row multiplied by a constant c. Well, guess what? Then it's again the operation is still linear. So it respects the linearity of that. So determinant of the matrix on the left is the linear transformation, right? It's a linear operation. It gives you the determinant of the original matrix plus c. There's the determinant of of the matrix when you have determinant. We have two rows R1 and R1. And we just talked about that because two rows are the same, this determinant is equal to 0. So therefore, determinant does not change, right, if you add in multiple of one row to another. So you can do it, you can do this. So in other words, row reduction procedure does not change the value of the determinant, right? So swapping rows negates the sign. Here's summary. Rescaling a row rescales the determinant by the same factor. Adding a multiple of a row to another preserves determinants. And determinant of a triangular matrix, in particular, if it's an echelon matrix, is the product of its diagonal entries. So to compute the determinant of a matrix, we first row reduce it and keep track of any row switches or rescalings of rows, right? Because we need to, this minus signs will accumulate, we need to keep track of them. And in the end, we multiply together inverses of the row rescaling factors, the diagonal entries of the final echelon matrix, and the -1 to the number of row swaps, right? So if we did any row swaps, we have to count them, and then if the number is odd, we multiply it by -1. If the number is even, we don't do anything. And well, that will give us the determinant of the original matrix. So of course, it will be much easier to calculate the determinant of the echelon matrix in echelon form than that of the original form. Yeah, as you mentioned, the summing of all terms becomes much harder. Okay. So if now let's have matrices EAM, E swap, and E scale of lambda elementary matrices, which are obtained by adding a multiple of one row to another, swap two rows, and rescale one row by lambda. Right, so and so here is the so E here is the, remember, E is the matrix which has which is the identity matrix, right? So the so E itself here, right, is matrix 1, 1, 1, 1, 1 on the diagonal, and the rest is 0. Right, so if we swap rows, if we add a multiple of another row, the determinant does not change, so we get 1. If you swap them once, we flip the sign, and if you multiply one row by lambda, then we just get lambda in the determinant. Yeah, so that follows from the rules that we just had. Okay, now if there are E1 through M are elementary matrices and M is any square matrix, then well, the product determinant of the product of this matrix is equal to the product of the determinants. And that follows from the previous slides, right? So we have seen that each row operation changes the determinant by multiplying the determinant of the corresponding elementary matrix, right? So these are, remember, these are the matrices that provide us with the row reduction transformations, right? So we swap rows, right? Multiply them by a constant, add multiple of other rows, and therefore every time we do that, the determinant is equal to 1 or minus 1, or is equal to lambda, where lambda is the scale. Okay, so that's how we get the formula for the determinant of the product. Yeah, like this. So in other words, it's another way to say information on the previous slide, right? So that to calculate the determinant, you need to keep track of all these row operations, and then if you multiply it by some scalar, you need to reproduce it here in the determinant. Now, invertibility. So theorem: a matrix is invertible if and only if its determinant is non-zero. Proof: the determinant of a matrix is a non-zero multiple of the product of the diagonal entries of its row-reduced version. You just see that. And of course, it's not zero if and only if the pivots run down the diagonal. That is, there is one pivot in each row and each column. And that means that it's invertible. So it's as simple as that. Now, let's talk about products. So if two matrices are invertible, then so you can write them in this order. Right? So AB multiplied by A minus 1 and by B minus 1. So AA minus 1 is equal to 1. And then BB minus 1 is equal to 1. So everything is equal to 1. And you can also do it in opposite order. So AB is invertible and B inverse A inverse, it's inverse. So the inversion, if you have product of matrices, right? So then inverse of A times B is equal to A inverse B inverse. So if they're square matrices, it's enough to guarantee that they're both invertible. Now, another theorem about determinants and products. So for square matrices A and B, we have determinant of the product is equal to the product of the determinants. Well, if any of these matrices is not invertible, then both sides are 0, because determinant of a non-invertible matrix is 0. If the matrices are invertible, then A and B can each be row reduced to the identity, as we have seen. And that means that we can write them as a product of these elementary matrices E1 through EA and F1 through FB, where these are elementary matrices corresponding to the respective row reductions. And then we just can calculate, right? So that A dot times that B is equal to product of the determinants, and these are, of course, as we have seen, they factorize right into the product of determinants of each of those elementary matrices. Now, and of course we can combine that back, right? So once we have this form when it's a product of all elementary matrices, we can assemble back together in a single product, which of course gives us determinant of A times B. Okay, so that's it for today's lectures. It was pretty fulfilling, so please make sure that you check the homework problem and then prepare your questions for the office hours. And we'll see you next time.